Hello everyone, today we are going to talk about how we can represent graphs in our code. Let's first talk about one popular way of representing graphs that is called adjacency matrix. In this case, we have a 2D matrix with the number of rows and the number of columns equals to the number of vertices. In this case, each cell will contain a 0 if there is no connection, or 1 or the weight that we are considering if there is a connection. For example, we can check for the node 1, we can consider the row number 1, and we see that we have a 1 that relates this node with the number 4. And in fact, there is here a connection between these two vertices. We don't have a connection with the number 0, and we can check that we don't have this edge here. Another way of representing graphs is using an adjacency list. In this case, we have a list or a dictionary that will contain for each position the vertices that are connected or that are adjacent to this node, that directly connected or adjacent to this node. For example, we have here, if we focus in the node number 2, we have two edges that connects this node with the number 4 and the node number 5. Let's talk now about the cost of each representation. If we talk about the adjacency matrix, it will have an spatial cost that is related to the square of the number of vertices that we are considering, as we have to store the matrix. This is good for dense graphs where we have to allocate a lot of edges. And this is providing a method to get the edges that is constant, because we have only to check for a particular position in this matrix. On the other hand, the adjacency list will have a special cost that is related to the number of edges plus the number of vertices. In this case, we have to store only the edges that are actually in the graph. This is good for sparse graphs because we don't have a lot of edges, and this is good for iterating over edges from a particular vertex. On the other hand, getting an edge is linear with the number of edges for a particular vertex, with the degree of a vertex, because we have to iterate over the adjacency list for a particular vertex. Let's see how we can implement this in Python. We have selected here a directed graph using an adjacency list. In this case, we are including here the dictionary that will map from one node to the adjacency list for that particular node. We can obtain the number of nodes, getting the length of this dictionary. We can get also the nodes, retrieving the keys of this dictionary. We can compute very easily the out degree, that is just checking the length of the adjacency list for a particular vertex. But on the other hand, computing the in degree involves more computation, because we have to iterate over each value, checking if this node appears or not in the list of adjacencies in the other vertices. We can obtain the number of edges. This also requires a for loop in order to iterate over each node in order to compute the out degree. We can add a new node here that is including a new entry in this dictionary. We can include a new edge that is just adding a new element to the adjacency list of a particular vertex, and we can retrieve the weight, this for a particular edge, and this involves iterating over this adjacency list in order to find the vertex that is connected to the original vertex. Thanks for watching and see you in the next video.